Afternoon. Dr. D.
What's up?
I had a question. So I had one of the class problems for today, and I obviously tried working on it, but I couldn't finish it. Is that all right?
Yeah, it's fine. It's fine. Same rules as last time. Get as far as you can get, and then you'll be all right. It's asking that you guys try. All right. Seems like it's 12:30. Let's get let's get started. Lord, thank you for bringing us together this afternoon. Thank you for the promise of the weekend. Lord, I pray that you would uh, just give us some time this weekend that we could reset ourselves, get our thoughts together, help us to accomplish all the things that we need to do. Um, Help us to rest, help us to prepare ourselves mentally to be back on campus, help the move-in process to go smoothly, help us to hit the ground running when we do our split sessions next week. In your name we pray. Amen. Okay. So we got a lot of stuff, man. We got a lot of stuff to do. We'll go over some of the timeline stuff later. So there's that. We're going to recap last class, and then today we start talking about electromechanical systems, right? What happens when an electrical system and a mechanical system love each other very much? And then we're going to do some example problems. That's what we're going to do. Op amps are confusing to people. Op amps are operational amplifiers. They are used for filtration and signal processing. We're going to watch a video in a second, so I'm going to defer this question until the video is done. And then if you still have questions, then you can ask them certainly. Scar is Simba's uncle from The Lion King. So there's that. He's not a good guy, man. If you guys watch Lion Guard, which you probably don't because you are aged out of that, but if you do, that's cool too. It's a good show. My kids like it. Scar comes back in The Lion Guard. So sorry, spoilers, I guess. So this class has big spoilers for Lion Guard, guys, if you haven't watched it. I apologize. KCL truths. So the Kirchhoff truths, right? We've got some of the current entering a node is equal to the current leaving the node, right? We're going to get more practice with this over the next couple of classes, okay? So one of these things, I think where the key here, the key confusion is, how do I know to use KCL versus KVL or both, right? How do I know? That's a great question. Remember, for an electrical system, we have increasing order of complexity, meaning increasing order of our system every time we have an energy storage unit. Every time we add a capacitor or an inductor, we go up by 1. Every system, since those are all defined by first order differential equations, we need a minimum of that number of equations to fully describe our system, right? So if I have a third order system, I need 3 first order differential equations to accurately describe what is going on in that system, right? That's what it means. So how do I know to use KCL or KVL? It's kind of tied into that. Well, first of all, the big clue is, are there any nodes, right? Do I have any junctions where there is 3 or more wires attached to it? And if you don't have any nodes, then you shouldn't be doing KCL because it doesn't buy you anything. It's a trivial equation at that point. If you have more than 3 nodes and you have multiple energy storage elements, you're going to need to use a combination of KVL and KCL. Remember, the name of the game in this class is that we are modeling all electrical systems in terms of our input variable, so either E in or I in, and either E sub C or E or I sub L, right? Those are it. Those are the dynamic variables for electrical systems. You don't have to wonder, well, should I be doing this in terms of the voltage drop across the inductor? No, you shouldn't, because I told you to use the current, right? So that's the thing. Make sure that you have as many first order differential equations as you have order of the system, and make sure that you can write, and essentially you'll always need to combine both KVL and KCL for pretty complex systems like second order or higher. You're probably going to have to combine them, all right? But let your dynamic variables be the guy, right? Remember, once you write down your inputs and your outputs, that's just focus on using algebra to turn all of your other variables into those variables. You guys have any other major things that you want to talk about before we get into op amps and doing some more review from the last class? No. It's all right. It's all right. All right. So you guys remember about op amps.
We're going to talk about the operational amplifier, or op amp for short. And this is the workhorse of all analog electronics. And the operational amplifier, it's a type of amplifier. An amplifier is anything that you put an electronic signal in and you get out a larger version of the signal. So this would be an amplifier with some sort of gain. And if I put a signal X in here, usually a voltage or a current, then the signal that comes out here is A times X. And that's what we mean by amplification. And a signal that I've shown here as X is anything that we're interested in. It could be a voltage or a current. And when we put it through an amplifier, we get a larger version of it. So this is a really common activity in electronic design. Now, when we talk specifically about an operational amplifier, the symbol for that we use for an operational amplifier is a triangle. And it has 2 inputs. One is the plus input, one is the minus input, and it has an output. And it also has 2 power supplies to it. There's some sort of plus voltage that goes into it, and some sort of minus voltage. So this is the abstract symbol for an op amp. So when we say the word op amp, we have some specific properties in mind. One is op amps have high gain. So in this case, the gain, usually with the symbol A, is something like 10 to the 5th to 10 to the 6th. Really, really high. Another thing we think about when we talk about op amps is that they're used for feedback circuits. And we'll talk about feedback in the next couple of videos and what that means. But that's the application that we use op amps for. And the third thing that's distinctive about op amps is that they have this kind of input. This kind of input here is referred to as a differential input. So an op amp usually has differential inputs, and that's as opposed to something we call a single-ended input, which would be just one wire. And what a differential input means, it says we can label the voltages here. We'll call this V out, we'll call this V plus, and we'll call this input V minus. And differential input means that V out equals the gain times V plus minus V minus. So the output signal here is proportional to the difference in the voltage between these two signals here. So I want to make a plot of this equation right here, just so we get a good idea of what it looks like. And the axes here are V in and V out, where V in specifically equals V plus minus V minus. V plus minus V minus, that's the input signal to the op amp, and we're going to apply the gain factor to it to get V out. And so that'll look like this, something like this. It's going to be a very steep line, and the slope of that line, the slope of this line is A. So the slope is going to be 10 to the 5th or 10 to the 6th, something like that, very, very vertical. Now, one of the properties of this is that V out cannot go above or below its power supply voltages. So on this plot here, that's called saturation. If V out gets up to V plus, we say it saturates and looks like this. It goes flat basically here and here, where this voltage value here is minus the power supply, and this voltage right here is the positive power supply. But over this range here, over this range in here, between those 2 points, it's quite linear. It goes through 0, and this is where we use it most of the time. So now I want to talk a little bit more detail about what this symbol means here and what's inside it and how it's actually connected up in a circuit. So we talked about the voltage behavior of an op amp. This is V plus, V minus, and V out. There's one thing more that we need to know, and that is the current. This current right here and this current right here for an op amp, an ideal op amp, is 0. No current flows in here. So this op amp is just sensing the voltages at these points, but no current flows in. So this is the second key property of an op amp. The first one is the voltage behavior. V out equals the gain times V plus minus V minus. Another way we can write this is V out equals A times V in, where V in, of course, equals V plus minus V minus. So these are the two electrical properties that are going to allow us to analyze these circuits. And analyzing the circuits is actually going to be pretty simple. So you're probably wondering, like, what is inside here? What's going on inside here? So what's inside here is somewhere between 20 and 50 or so transistors and resistors, sometimes capacitors. These are really complex designs. And for right now, if we just concentrate on the two properties that we have here, we'll be able to use these circuits even without understanding exactly what's inside. Suffice to say, it's a differential amplifier with really high gain. And with just that knowledge, we can work out how these circuits work. So let me do a couple of more details on how this thing is actually hooked up. So we have a plus terminal and a minus terminal. There's more terminals on this. There's a power supply like this that's plus big V, and there has to be a minus supply, typically a minus supply minus V. And there'll be a ground pin. There'll be a ground node on here, like that. And when this is used in a circuit, there'll be, over to the side, there'll be two power supplies. And this will be 12 volts. 12 volts is a real typical value. And there'll be another one. And this is a plus 12 volt supply as well. And they'll be connected together. And this node right between them will be our ground node. That's the voltage reference. And these two guys will be hooked up like that. The two power supplies will be hooked up this way. So with respect to ground, this node is at minus 12 volts. And this node from ground is at plus 12 volts. And ground is right in the middle. And when we measure V out, we'll measure it with respect to this ground node. So this is the voltage where we measure plus or minus V out right there. And what we're going to do is we're going to assume that all of this stuff is always hooked up. And we're just going to use an even simpler symbol. Just the three terminals like that. And you'll know that all the rest of the power supply is hooked up that way. And the thing to keep in mind is there's a large minus voltage, there's a large plus voltage, and the ground level, the ground node, is right in between. So positive voltage is high on the page, negative voltage is low on the page, and V out can go both positive and negative around ground. So that's your voltage framework to keep in your head. And the op amp that we've been looking at has a symbol like this. And we know that V out equals some huge gain times V plus minus V minus. So this is a differential input. Here's V plus, here's V minus. One way I think about this is to look at the way a change in voltage on the input modifies the output. Let me label V out here. So if there's a change on the input, say V plus goes this way, because it's a plus sign, that means that V out goes this way. Now, if I change it over to V minus is on the negative input. If V minus goes up, then V out goes down. So that's the inverting, it's called the inverting input, and this is called the non-inverting input. So on the non-inverting input, up goes up, and on the inverting input, if you go up on the inverting input, you go in the opposite direction on the output. Let's say that the positive input, the non-inverting input, went down this time. And that means what? That means that V out will go down. And just do the same thing over here. I'm going to run out of colors. Let's do the same thing for the inverting input. If the inverting input goes down, what does the output do? It goes up. It goes in the opposite direction. That's a way to think about this symbol when you see it on a schematic page, is how do these signals translate through the device? Positive non-inverting signals go in the same direction. Inverting signals go in the opposite directions. Okay, and here's one final trick I want to share with you, something to be aware of. You're going to see a symbol like this on a page. The same op amp. It's the same op amp, but it's written on the page with the negative, with the inverting symbol on the top and the non-inverting symbol on the bottom. So as you look at a schematic that has an op amp in it, one of the first things you want to do is just glance and see what order these symbols are in. Or does it look like that, or does it look like that? And keep that in mind as you're reading the circuit and trying to understand what it does.
Right. So like for us, right, we're always going to see them looking like this. The non-inverting on the bottom and inverting on the top. All right. Cool. You guys have any other questions on op amps for right now? No, not really. Okay. Sounds good. Question. All right. So here we go. We are going to do some time trials today. Right. You guys know the rules. Here's the points. Let's do the thing. You're going to get 45 minutes to work through this problem. 45 minutes in your groups to work through this problem. It's an op amp. Hey, guess what? You need to make a model relating E in to E out. That's what we need, right? I'll give you guys a minute to write this down. I will set this up as a 45-minute breakout room, as I can. Give you a minute, then I will hit the open all rooms button. And guess what? The rooms, they will open. It's not a clever name. It's a trick. All right, I'm opening the rooms. There we go. All right. Cool. So everybody got there. So that's awesome. Good work from everybody. So let's talk about it, right? We'll just run through it again just to make sure, right? So here's my circuit diagram. Excuse me. What do I have? Well, we've got I1, IA. I've labeled this node here A. I've got I2 going across resistor 2. I've got I3 going through my capacitor. Okay. Cool. Right. And so one thing that I hope you guys noticed was this is pretty much exactly like the problem that we did in class on Tuesday, except that I added a capacitor, right? The one that we did in class was just R1 and R2, right, with no capacitor there. Now, if we go back and we check that problem, right, we should see that we got negative R2 over R1 E in is equal to E out, right? And so basically by adding a capacitor, we have the same base system. We're just going to add the response of the capacitor to that, right? That's all that's going to happen. All right, so let's see. Let's see. What do we do from here? So we got my inputs and my outputs, right? Well, all together, what are my inputs? What's my input?
In.
T.
Yeah. All right. What's my output?
E naught.
Remember, this is the thing that comes up a lot, right? Because I told you last class, right, we're going to use EC and IL, except for the case of capacitors, right? And there's a real world physical reason for that, right? With an op amp, right? With an op amp, we are trying to amplify or filter our signal, right? We're trying to process this signal in some way. And so we are interested in how we are processing our input signal and how that becomes our output signal, right? That's what we're interested in, right? So that's why we do it in terms of E in and E out. For standard circuit problems that don't have an op amp, do it with E sub C and I sub L, right? So what are my mathematical truths? Well, let's write the easy one first, right? KCL at, and that's going to tell us that I1 is equal to IA plus I2 plus I3, right? So the sum of my current coming into my node is equal to the sum of my current leaving my node. Could have also written this like algebraically differently, like I1 minus IA minus I2 minus I3 is 0, right? It's all the same. It's all the same. All right, I'm going to reserve a spot for my op amp truths. Before I do that, I know I've got I sub C is equal to C, E dot C. I've got ER1 is equal to R1, I1, and ER2 is equal to R2, I2. This guy is also equal to I3, right? That capacitor current is just I3. My ideal op amps, what do they tell me? Well, the first one is that IA is approximately 0. The other truth that we're going to exploit here is that EB minus EA is equal to 0. So therefore, EB is equal to EA, right? So what is EB in this? If we look at our diagram, what is EB?
0.
0, right? It's connected to ground, which therefore tells us that EA is also equal to 0. The third truth is that K is infinite, but we don't really exploit that one very much or ever, right? But it's there. It's there. We're not going to use it, so I'm going to leave it off. Okay. So we should have everything that we need now, right? I think that's it. So we can start our reduction. And where do we start our reduction? When we start it with our KCL. And KCL tells us again that I1 is equal to IA plus I2 plus I3. Well, I have expressions for all of these currents, right? We know that this is going to be 0 based on our ideal op amp rules or truths. I know that I1, well, if I rearrange Ohm's law, right? This is ER1 over R1 is equal to ER2 over R2 plus C E dot C. That's just plugging in. That's doing a little bit of algebra to Ohm's law and then plugging things in for current, right? That works. Okay, so that's fine, but we need things in terms of E out and E in, right? So we're gonna exploit that other trick that we used last class, right? Where we talk about voltage drops. And you guys did a good job and you all remembered, but let's just go over it again, right? So what is a voltage drop, right? The voltage drop is the amount of voltage that I am losing as I cross an element, right? So this is going to be E in minus EA, right? So ER1 is equal to E in minus EA. I had a person in the class earlier today, my other class, ask, well, do you need to write this down as a mathematical truth? And in my opinion, you do not. And the reason is that this is just an algebraic redistribution of what you already have in your truths, right? This is an algebra step. So if you don't include this in your truths, that's fine. I don't have a problem with that. But you need the major things in there. Now, this also exploits some of the geometry of circuits as well, right? Because EA minus E out is the voltage drop across R2, but it's also the voltage drop across the capacitor. And the reason for this is because they're parallel, right? And if they're parallel, they both have the same potential, right? Which means that they're both going to distribute the same amount of voltage as we go across them, right? All right, so here we are, right? So we know ER2 is going to be equal to EA minus E out. But what about C? And this is something that you guys all thought through on, right? We all thought through it already. So I don't really need to go back to it. But remember, our currents, right? The current equation, the ODE, the ODE for a capacitor is this. IC is equal to C E dot C. So knowing the voltage drop is great, but I need the derivative of this voltage drop, right? I need ddt of EA minus E out. All right, well, these are both functions of time, right? So this is the same as writing this. Now so this is equal to E dot C up here. Okay. Okay, cool. Right, we all went through this in the group breakouts. So if I come back to my reduction, I can plug in these things now, right? And I can get E in minus EA over R1 is equal to EA minus E out over R2 plus C E dot A minus E. Well, we established that that's 0. What's the derivative of 0? What's the derivative of 0?
0.
If you're watching this later, throw the derivative of 0 in the comments. Man.
It's 5.
5
41st millennium.
It's 5 zeros, Trevor. 5 zeros. Okay, cool. All right, cool. So now what, right? Well, E in over R1 is equal to negative E out over R2 plus C, minus, right? That's a minus, not plus, minus C E dot out. And you could leave it like that. That would be okay. I'm going to polish it though, because for reasons that we'll get into later, not today. It has to do with putting things in the standard form for a first order differential equation. So I'm going to polish mine and I'm going to have it like this. But these are algebraically equivalent, and I'm happy because you've got inputs on one side and outputs on the other. The one in the red box just looks nicer, in my opinion. I want you to notice, just like I said earlier, just like I said when we started talking about how to do this example, this is the same. If you take off that capacitor thing, if you made your capacitance 0 because we didn't have a capacitor, right? You're left with the same exact equation that we had when we did it in class on Tuesday, and it was just the resistors. So adding a capacitor literally just adds the capacitor response to this equation, which is what? Well, that's just superposition. It's just. You guys have any questions on this one? Not too bad, I hope. There's definitely an op-amp problem on the homework. So be aware.
I have a question.
Yes.
So on Tuesday, we talked about how whenever we add a component, that it's going to increase the order or the system of the system of equations that we're working with.
Yeah.
If we are doing, for instance, a filter where we add an inductor and a capacitor, is that same idea for the op amp?
Yeah, right. So we saw that already. You had for this particular example, right? You started with a system that was 0th order, right? Did not have a derivative term, and we ended up with a first order differential equation, right? So if you add more, the more elements you add, the higher the order is going to become. Right. What's going to happen? Good question. Again, you can see with electrical systems, right, how they get very complex in terms of the order of the system very quickly, right? Because the more capacitors and inductors you add, the more energy storage you have, the higher the order is going to be. Cool. Any other questions?
What's the highest order that we would experience in this class? Like, would we go like 5 or more even? I don't know.
Well, Noah, that's a good question. I had in graduate school, the guy who taught our controls class would routinely give us 20 plus order systems for exams. We're not going to do a 20th order system. If you guys want to see what that looks like, I can dig up an old test and show you. It is, yes, Taylor, 100%, very gross. It is, and we had to do things like root locus diagrams by hand, which, you know, doesn't mean anything to you guys because we're not going to cover that in class here, but it's a pain. Let's just say that. It's a pain in the butt. So what are we going to do? Right? For right now, the highest order that you'll probably see in class, right, honestly, is probably going to be, by the end of this year, we'll probably do a 4th or 5th order system at highest. They're time consuming. Remember, I only have, you know, 2 hours, 2.5 hours to give you guys stuff to do in class. I'm not really interested in spending most of that time, you know, having you guys do super high order systems, right? It's not beneficial. It doesn't test the concepts appropriately. And there's other reasons why we'll talk about when we get into analysis, right? Why talking about a 2nd order response is typically sufficient. Good question. So 100th order system on the first exam, right? And you guys just get as much of it done as you can by hand. It's fine. 50 mass elements. Okay. All right. Anyway, any other questions? Don't forget to do your ethics paper this weekend, please. Ethics paper due on Sunday. Homework 2 due on the 4th. Exam 1 on the 8th and homework 3 on the 11th, right? So this is where I'm going to talk to you guys a little bit about how we're going to schedule the next few weeks, right? So next week, obviously, half of you will start coming into class on Tuesday, half of you will come on Thursday. It'll be the same setup when you're not in class. I'll have the camera probably here. I might put it on a tripod over there. We'll have to see, but the screen will be shared, right? I'll have to talk louder, so when you're in class, you will think that I'm yelling at you. And when you're out of class, you'll hear me just fine because I'll have a mask on while I am trying to speak into the microphone, right? Anyway, this week, we're obviously right now going to talk about electromechanical systems. We're going to tie that up next week on Tuesday, and then we're going to start thermal and fluid systems on Thursday next week. That's our plan, right? So we start that Thursday next week. You will get 2 full lectures of thermal fluids, which is what you're going to get anyway, but we'll have the exam on Thursday, and your homework for topic 3 will be due after the exam. Okay.
Will fluids and stuff be due, or like, will that be on the exam?
It is exam eligible, yes. Yes. Everything in the first 3 topics can be covered on exam 1. I mean, it's kind of, I feel like it's kind of obvious, but just to say it out loud anyway, this is a class that builds, right? So in order to analyze something, you're going to have a model for it. So it's not outside of the realm of possibility on concurrent exams to for me to ask you to model something and then take the responsibility, right? It all builds on it. So don't think that modeling is just gonna go away, right? That's not how it works. But that's what we're doing. Make sure you're using office hours. Come get your questions answered and all that stuff. All right. So why don't we talk about something that's actually that's not op amps and not circuits, and that you guys might find slightly more interesting, maybe. Right? Electromechanical systems. So what is an electromechanical system? What is it? And this is the part where somebody wants to give me a wise answer and says, well, it's a system that is electrical and mechanical together. And yes, that is true, but it's also extremely unhelpful. What is an electromechanical system? Well, it's a system that is designed to convert energy from electrical to mechanical or mechanical to electric, right? These are super common systems that we see all the time. So somebody, please give me an example of a real world electromechanical system.
Motor.
What was that? Sorry.
A motor.
Motor, exactly.
An actuator.
An actuator, yep.
Generator.
And a generator, sure.
Motor.
You guys nailed it. All right, so yeah, you got motors and generators. Motors and generators are basically the same thing. They just run in opposite directions, right? You got actuators, sensors. Right? Most sensors are electromechanical, like a strain gauge, right? You're gonna have some physical deformation that gets picked up and turned into an electrical signal. You got speakers and microphones. Yeah, yet another set of devices that are just the same thing but run in opposite directions, right? Speakers output vibration, right? Take an electrical signal and output a vibration. Microphones intake a vibration and output an electrical signal. Right? If we combine mechanical and electrical elements, then we can get a variety of useful electromechanical devices. A couple of them are up here, like rotary to linear actuators and solenoids, right? Solenoids. The good news is, because they are both mechanical and electrical, you get to use Newton's laws and Kirchhoff's laws together. I know everybody, you're all very excited about that, right? I know, right? So we've got more mathematical truths that we can use. It's fantastic, right? So what? How? How are these things interacting, right? Electricity is not a physical thing, right? So how does it interact with the real world, right? Dr. D, I don't believe you that electromechanical systems exist. It's dark magic, and they should be abolished from the face of the earth, right? That's how everybody feels. I know, it's true, they should. But just in case they're not, let's try to understand how they work. So they're going to be coupled through magnetic field interactions, right? So an electric current establishes a magnetic field. Right? So we're going to talk about the three basic relationships between current and magnetism, right? So right off the bat, an electric current establishes a magnetic field. If you have a length of wire and you run some current through it, you're going to establish a magnetic field. It might not be a strong field, but you will establish some field. The second one is that a current carrying wire in a magnetic field has a force exerted on it. Well, this is a direct function of our first, of bullet point number one, right? Why? Because if I have some current going through my wire, I've already established a field, right? That field is then put into another magnetic field, which those two magnetic fields are going to interact, and it's going to create a force that's exerted on our wire, right? And then there's the third bullet. A wire moving relative to a magnetic field will have a voltage induced between the ends of the wire. So if I have just a plain old wire and I move it through a magnetic field at some velocity, I will get a voltage to be induced in that wire. Those are the three things that we're going to exploit to create a coupling system between electrical and mechanical systems. I'll use this time to say that the reason that I went for my mechanical engineering degree and not an electrical engineering degree is because my brain is much better when I can visualize what I'm working on. I find that I can more easily visualize a mechanical system than, how magnetic fields are going to interact. And so I understand, right? I understand that some of this is going to be hard for you to visualize, right? And I get that. And then that's part of the challenge here, right? But we can do it, right? We just need to try it out, right? So first one. I've got current flowing through my wire. It's flowing in the upward direction. The Biot-Savart law describes this magnetic field. We'll call it B. The larger that B is, the larger the field is, right? This B is our magnetic field density. The direction of the field lines are defined by the right-hand rule. And in this case, that means that if you're holding the wire with your thumb pointing in the direction of current, the direction that your fingers are curled in is the direction that the magnetic field is traveling. That's the direction of the field lines. Okay. Cool. Although not really immediately helpful, right? Because it doesn't give us a relationship for how B changes as a function of any of this, right? But cool. We can work with it. All right. So that's neat. We can figure out what direction our field lines are, right? What about bullet point 2? A current carrying wire in a magnetic field has a force exerted on it. Well, I'm going to take that same wire that I just had in the last drawing. And remember, if my current is traveling in this direction, if I'm holding the wire with my thumb pointed that way, I should be getting a field in this direction, right? Curling around this way, because that's how my fingers would curl around. Okay. Okay, so that's my field. And notice that field is going to interact with this other field, right? And will produce a force, right? So the equation for an induced force due to a magnetic field is I times L cross B, where I is my current, L is the length of the wire, and B is my magnetic field or my magnetic flux density. Now, for the special case where my wire is perpendicular to the magnetic field, I can simplify this equation and I can turn it into F equals B times L times I. This is dark magic, right? This is, Voldemort used this to enslave the Muggles, right? And all that. I don't know. He probably did. Right. This is how we end up with something that is not tangible to us, right? Electricity, something that we cannot see with the naked eye, but yet it is still exerting some force in the real world, right? On a real object, on a mechanical system. And this is how we're going to couple the amount of current, right, that we have here to the amount of force that we get. Because notice this equation tells us what? The more current that we put in to our system, the stronger the force is, right? The more current we put in, the stronger the force. The longer that wire, right? The larger, that just means that our field is larger, right? Then the more we will get out of this. As this is the basis for electromechanical actuators. Or what about if I'm moving the wire, right? I no longer have current flowing through this wire. I'm just gonna pull it up through this magnetic field, right? And I can create an induced voltage. We'll call it E sub B, and that is the velocity of my wire cross the field flux density dot L. And if it's perpendicular to the field, then we get E sub B is equal to B times L times V, right? Where E sub B is what we call the back EMF, B is my field density, L is the length of the wire, and V is the velocity. These two equations that we just went over for force and for back EMF are going to be the basis by which we form mathematical truths that couple electrical and mechanical systems. Because notice, this back EMF depends on my physical response. Depends on how fast I'm pulling this through. Depends on the velocity, right? My force, my physical response depended directly on my electrical input, my current. Right? So these two things are intertwined in this case. Right? Do you have any questions on these so far? We're doing okay. Maybe. In that case, let's watch a sweet video about how motors work. Because Mr. Wizard is the man. If you don't know Mr. Wizard, I'll just feel sad.
That's my homemade motor based on wire on front. What's it called? Weird? Weird. It's not weird. It's just a motor. But that's your word for great, good, or something weird? Okay, I'll accept it as a compliment. You can build one of these yourself out of stuff you can sort of find around the house. But first, I think you should make sure that you understand the principle of what makes the motor work. See that magnet over there?
Yeah, this one?
Right. Well, this one's sitting on a turntable, so it can spin around. If you bring the north pole of one magnet near the north pole of another, wow.
It repels.
Yeah, repel. Then, you see this turn, if you now bring the south pole around like that, it's gonna give it another spin.
Oh,
Yeah,
yeah.
you get it to spin, see if you can get it there. That's the principle of the motor. A spinning magnet and one that you can change the polarity.
Right.
And then you can get them in the right sequence while you can get the other one to speak. So let's now take a look at this one, because this is a sort of a real motor. You want to put that over there? Thank you. This time, the current's going to come through here from my power supply and go through there. What will not make that?
Like into an electromagnet, because like there's a lot of coil wires, and when an electrical current goes through lots of coil wires, it makes into an electromagnet.
And not only that, but see how this is curved around right here, the magnetism is going to come up. This is all going to be coming back. So is that.
Okay.
And here, I'm going to use my paintbrush as a pointer, because the important part is going to be kind of hard for you to see. I want you to be able to see it. First of all, the easy one, where is the magnetic spin?
Right.
They're electromagnets too, they're coiled.
Right.
Now, what is the word community, you know?
It means that somebody that's on a train and goes to work and comes back.
Back and forth, back and forth. Well, it's just the same root of the word, but it's called a commutator. It's the thing that reverses the polarity. You see this right down here, the shiny part right there?
Mm-hmm.
Okay, there's a little piece of metal that rises against it, so current can go through there and make this into electron. Now what? It goes through a slot there.
Mm-hmm.
Okay, now it's making contact with this, and that makes this into a magnet.
Right.
Then the next one comes around, there's one about the slot, and that makes, now you make this into a magnet. So that's reversing the polarity, and that's why it's called a commutator. All we have to do is add a little current.
And turn on.
There you go. Now see if you can find the important parts of the motor right here, because this is from an actual real motor, but I took it apart so that you can see the important parts. First of all, where's the spinning?
Right. They're the ones that like.
Right down here.
And then there's the post wire. Actually.
Then here's the commutator in this case. See that little black thing right there?
Mm-hmm.
That's a carbon brush, a hunk of carbon. Current can come up through here. Now the carbon touches this part right here. Current can come up on the other side and touch that one over there. So that's how the current is reversed, is this spin.
Okay.
Okay? What's missing?
The stationary one.
Okay? There's one right there. I'll turn on the current. You hold this magnet up above.
Wait, if you can feel the electricity. Alright, let's get away.
Okay. Now that you know all the important parts of the motor, come on over here and see if you can figure out how to build one of your own.
Okay. First of all, you need the stationary magnet.
That's the John magnet down below.
And then you need the electromagnet that wants to
The
spin.
spinning magnet, that's gonna spin right there.
And then there's like some electricity there. Right? And then there's wires that come up. And
What's
then
missing?
the commutator.
Yes. You can show you, this is a very clever thing that my friend Bud Lynch put in. See that wire down there?
Mm-hmm.
Well, part of it's dark. See how it's dark on one side?
Mm-hmm.
That's a nail, which works like an insulator. But you scrape off part of it, so when you turn it the other way, you see how it's scraped off and it's shiny?
Mm-hmm.
That means current can flow. Whenever the shiny part is touching the top of this end of the safety.
It's like a pulse.
So, yeah, current can go through and give it a pulse. It goes down here through the other side. Then when it's like this, no current goes through. Then when it comes around again, current goes through. So that's the secret of this homemade motor. Connect it up, see if it will actually go.
There's a stationary.
Yep. Right. Look at those, there you go.
Hey.
So you can make your own homemade motor with a permanent magnet, a coil wire, a safety thing, and that.
I'm gonna make one of those at home.
And you should too. Right now, make one about with whatever is in your room. It's fun. All right, so that's how a motor works, right? So let's talk a little bit more in depth about the parts of a motor. And so we're going to talk about DC motors in this class. Most of all the models that we make, if we're using a motor, are going to be for DC motors. You can see here, what do we have, right? We've got this right here. This is our stator. right? The stator is another name for the stationary magnet, like we saw in the homemade corkscrew version of the motor, right? That's our stator. So the red area is our stator. The inner part right here, this is called our rotor or our armature, right? In here. And typically, there's a reason why I'm drawing this like this. Imagine these are coils of wire going around and around the rotor. The rotor is the central iron core, right? And, or whatever it's made out of. And the windings are just wire. And when you put them together, you get the armature. The armature is the entire assembly of the rotor with the windings, right? So that's our windings, right? So the armature of the rotor disc is wrapped with coil or wire called armature windings, right? So we've got some field being established by the stator, and at any point on this, we should be perpendicular to said magnetic field, right? We should be creating our own magnetic field through the rotating armature. Okay. So the armature windings on the top half of the rotor carry current flowing into the page, and on the bottom half, we have current flowing out of the page. Okay. This is going to produce a radial magnetic field that is perpendicular to the stator field, which is nice because that means we can use those easy equations instead of using cross products, right? So the total electromagnetic torque on the rotor can be found by T sub m, or motor torque, is just the force produced times R. Well, if we go back to a few slides ago in our notes, we wrote down that the force is just B times L times I, right? So this B times L times I times R is how much torque we're generating with our motor. Now I want you guys to notice something here, right? The amount of torque scales with a couple of different variables, right? It scales with our field density. The larger the field density, the more torque we get. The more length of wire that we use, the more torque we get. Right? The higher the current, the more torque we get. And the larger the rotor, right? The larger the radius of the rotor, the more torque we get, right? But there's a more convenient way of talking about motors than this, right? Because what if I wanted to go buy a motor, right? What if I wanted to go buy a motor? How would I determine how much torque I need, right? How much torque I want? Because no, I don't know if you guys have bought motors before, but if you do, it comes with a fancy motor performance curve that gives you the amount of torque versus how much current you put in, right? So we can rearrange B, L, and R. Right? We're gonna assume that our magnetic flux density, our magnetic field intensity B is constant. We're gonna assume that the length of wire is constant. Well, it should be, right? Because we're not adding or subtracting wire once the motor is built. And we're gonna assume that the radius is constant. Again, should be, right? So we're gonna call all three of those together K sub M, or sometimes you'll see it written as well as K sub T. This is either the motor or the torque constant. So look what we have here. Now we have this nice equation for motor torque that's K sub M times I. And if you've ever played with a motor, what have you found? Well, the more current you give it, the higher the torque that you get. If you look at your motor performance curve, right, typically it's linear through a range, right? It's not perfectly linear, but through a range, you have this linear performance, right? You have I versus torque. The slope of that line on your motor performance curve, that is K sub M. Typically we call it the motor torque constant. Has units of Newton meter per amp, right? Let's check that out. Newton meter per amp times amp. Yep, Newton meter. Units check. The units check. You know, the heavens open up. The sun shines. Angels sing. All that. All right. Is everybody all right with this? Right? It's pretty neat, right? We can scale our torque based off of the current, right? That's good. That makes sense, right? When we play with motors, that makes sense. So what about the other way? Right, because we have to deal with that back EMF. So how are we going to deal with back EMF, right? Because remember, it's also spinning, right? So all of those wires are moving radially inside this magnetic field. So whether or not you're giving them any current, if you can spin it, it's going to produce a back EMF, right? And our back EMF is B times L times the velocity, because it's a perpendicular, the field is perpendicular at all points, or therefore assumed to be. Now remember, from dynamics or physics 1 or wherever it is, right? The velocity at any point, right? The tangential velocity at any point on this surface is just what? Well, the velocity is r theta dot, r omega, r theta dot, which is just the same as x dot. And that's where that substitution comes from, right? BLR theta dot. Well, hold on a second. I've seen BLR before. Wasn't that my motor torque constant? Sure was. But it's also your back EMF constant, K sub B. That's B times L times R. So we can rewrite the back EMF equation, right? Where that's KB times theta dot. So turns out that we produce more back EMF the faster we go. We'll produce more back EMF the faster that we go. It has KB, right? Even though it is the same as K sub M or K sub T, has different units when we're talking about it in terms of back EMF. It's got volt second per radian. Right? It's a volt second per radian. And I know that you're all thinking, well, there's no possible way those two things could be equivalent. Well, it turns out that they are, and here's why. 1 volt is actually 1 Newton meter per second. Okay. So if you were to substitute that in on KB, right, to get 1, instead of a volt, we had a Newton meter per second amp times seconds times 1 over radian, right? Well, radian's a throwaway unit, so we're left with Newton meter amps. So it checks out, right? They're equivalent. So it turns out if you have the motor torque constant, you also have the back EMF constant. All right. Guys have any questions on this?
Real quick, what's that symbol that's equal to r theta dot on the left? Is that V or an R?
This?
Yeah, that.
This erase? That's my V. So let me
That's a V.
let me tell you. Let me show you something. Right?
Oh, okay.
This comes from back when I taught thermo 1 semester. I use volume. This is, if you see me write this V, that's volume. This guy is specific volume. And a fancy script V is for velocity. That's where it comes from.
Thanks.
No problem. I know, I've been told that it looks like R's or N's also. And to those people, I say, get your eyes checked. It's ridiculous. Okay. No, I can see it. All right, anyway. Any other questions here? Do you have any other questions? You guys are right here, right? I'm hoping that we've seen this before in physics too, a little bit, maybe. I don't know. I never took physics 2 here, so I can't speak to that. All right. So how does it work? So this video is going to go over the operation of an AC motor, which is slightly different than a DC motor. However, in general, the same rules apply. So let's take a look.
Electric car.
You guys are not getting audio or just audio?
Is it coming out of your speaker at your end? Because it just sounds terrible. Like we can't hear it.
Yeah, it's coming through your microphones rather than
Try
the.
this. Is this better? Whoa. Hold on. That's not what I wanted to do.
Yeah, there's a way to share the audio through.
All right. So, first of all, if you are relying on your battery packs for structural stability, I think we have an issue. Second of all, I definitely do not think that IC engines will be gone in the next 5 years. I don't see that happening. But you know, maybe I'm just not a futurist, right? Maybe I'm just.
Imagine something puncturing one of those cells, because that's lithium ion, right? So you just get that puncture and the whole thing goes up.
Exactly, and that's part of the other thing, right? Tesla's
Like the Samsung Galaxy phones a few years ago.
Boom.
Teslas are notorious for having their battery packs start fires too. Right? So it's anyway, it's fine. Okay, cool. So let's do a problem. What time is it? Yeah, we'll do a problem. All right. Here's the problem. All right. So what I want you guys to do, I want you guys to take. I'm gonna throw you back in your breakout rooms. I want to take 15 minutes. See how far you can get with this problem. All right. Take a minute. Write it down. It's an electromechanical system. And you've got your circuit side. So let me just say this before you guys get started, right? If you're feeling overwhelmed because there's two things on this diagram here, break it into pieces, right? Do an electrical system analysis and do a mechanical system analysis separately, and then see what happens. See how they can combine back together, okay? Remember, you guys have equations for TM and for EB, so you should be able to work through this. All right. All right. I'm gonna open the room, so you guys get 15 minutes, see how far we can get, and then I'll bounce around. I'm back. Happy Thursday, Friday, whatever day it is.
Did you know Geico is now offering an extra 50% credit on car and motorcycle policies? That's great. So what do you? You a scarf. I'll finish, Jay. Enjoy. Save an extra 15% when you switch by October 7th. So repelling down mountains.
All right, looks like we're back. I mean, 15 minutes isn't enough time. I was just trying to split the difference so you guys don't have to listen to me talk, right? And so you guys were working it, right? You were working it, and that's good. All right, so we've got to draw our picture, right? What do you guys want to start with? Pick your poison. Do you want to start with electrical system or the mechanical system?
Electric.
Electrical.
Yeah, electrical for sure. All right. Just so we have them. Do that. Here's R. Here's L. My current is I. We'll call it I sub A, right? For now. Doesn't really matter. It's, you know what, let's call it I sub L. Because that's what we're used to. We'll call it I sub L. Remember, it's the same current that goes through the whole thing, right? There's no junctions. There's no nodes. So the current never splits. Right? I mean, that's pretty much what we were given. I will do one more thing, right? Because we know there's no nodes, we're actually going to label our KVL right here. We're going to do a KVL on that. All right, well, that leaves us with our mechanical system, right? And in that case, our free body diagram, J, theta, and TL, right? So that's what we should have here, right? Oh, did I draw those in the, yeah, I got that in the right direction. Cool, cool, cool. All right, so you guys should have a free body diagram that looks like this, right? How do we know that? Well, if we look back at the schematic, they're all shown, right? It's shown which direction everything is rotating in. So how does an electric motor work, right? Well, we input, in this case, we're inputting some voltage, right? We're inputting some voltage. That's going to produce some current, right? That is going to create our magnetic field, right? And that field is then going to interact with the motor, right? And the motor is going to interact, and the mechanical side is going to interact with the electrical side through our back EMF, right? So what are my inputs and my outputs? What's my input? Let's talk about overall for the whole system. What's my input?
Ian.
Yeah, we've got E in. Could you make a case for E sub B? Sure. I mean, that's actually being input from the mechanical side, right? That's a voltage source as well. But really, what we're going to do is we're going to turn on our voltage source, and what are we going to get out? We're going to give this circuit E in, and we're going to get something. What's going to happen?
The current.
What happens to the mechanical system because I've introduced a voltage?
Eventually it rotates.
Yeah, it rotates, right? So we get theta.
Theta.
These are going to be my globals, right? This is what I'm trying to get in and out. What are my local inputs? Well, if I'm looking just at the electrical circuit, right? For just the electrical circuit, my input is E in, and my output, I call my EB, and my output is IL or IA, whatever you call it, right? IL. Right, this is just electrical. What about just the mechanical, right? What do we have coming in?
The torque. Yeah.
For just the mechanical, we're gonna have I sub L coming in, right? Which is technically I sub L, right? You could call it T sub M, which is a function of I sub L. And we'll get theta and some load torque out. Right? That's kind of what we're going for. Combination of theta and load torque. Right. So continuing with the theme of sticking with the electrical first, let's write down our mathematical truths for the electrical system. What do we have? Well, I've got my back EMF. I should probably write that down. And that's just KB theta dot as derived in class. I've got KVL. And KVL is going to be negative ER minus EL minus EB plus EN is equal to 0. ER is equal to RAI sub L. EL is equal to LI dot L. And that's it. That's all the mathematical truths that I have here, right? I've got my element equations for my resistor and my inductor. I've got my Kirchhoff's voltage loop, right? My Kirchhoff's voltage law. And I've got my back EMF equation, right? And I'll end up plugging those in a second. But before we get to the reduction, let's write down our mathematical truths for our mechanical system. Mechanical system, right? So what do we have? Well, we've got Newton's second law for rotation. I've got a damper. I don't have a spring here, but I do have T sub M is equal to K sub M times I sub L. Where does that come from? That's the motor torque, right? That's just the motor torque. Just the motor torque. And now we're ready. Now we have everything. Now we just need to do our reduction, right? So let's stick with the electrical circuit. Stick with the circuit because that's what we've been doing. All right, so for the circuit, right, we'll rewrite our KVL here. Okay, if I rearrange this a little bit, and
I think it's a positive EN.
yes, thank you. So I can rewrite this, right, by moving everything over and substituting in. We can do that. And I'm going to leave that like that. And I'm not going to touch that again. And we're just going to walk away, right? So what do we do with the mechanical system? We got to sum our torques. Well, if we look back at our free body diagram, T minus my load torque, that's T sub M, minus my load torque minus my damping torque is equal to J theta double dot. Well, I can plug some things in. And that's that. Dunzo. Complete. Okay, well, I mean, that's all well and good, right? That's all well and good. But in the real world, the amount of times you'll ever be asked to determine the position of a motor is basically zero, right? People don't care about the position of the motor in most cases. And I mean, I understand that there are times when you would want that, and that's fine. But more likely than not, we were going to want this in terms of motor velocity, right? So we need to change the dynamic variable. However, if you had left it here and here and you weren't instructed to do it, that's perfectly fine. But if you wanted to change the dynamic variable, how would you do it? Well, I just want to change theta dot to omega. So literally, that's what I'm going to do. Theta dot is equal to omega. So I end up with this. And for my mechanical system, so you end up with this if we flip our dynamic variable. Okay. Does have any questions on this? If you get a mixed system like this, right? What do you do? The first thing you do is you break it into its subsystems, and then you just analyze the subsystems. Right? Just analyze the subsystems. Break it into something that you know. Break it into something that you know.
So in every like example like this where we have a mechanical and electrical component, we should have at least two equations at the end.
I would highly recommend keeping your subsystem equations separate. Yeah. It's gonna get gross really fast, right? Because how do we? It's just not good, right? So if you either solve one for I sub L and then you have to take the derivative, or you solve one for omega and then you have to take a derivative, right, or an integral to get it back in. It's just, no, thank you.
It didn't look fun. That's why I was asking.
No, thank you. We'll do it with Laplace transforms, but that's because when we get to Laplace transforms, you invoke the dark arts and you make the sacrifices that you have to make, right? Like that's.
When do we use KT versus KM? What's the difference between the two?
KT and KM are the same thing. It's just whether you call it the motor torque constant and you use an M or you use a T. It's the same. I apologize for switching notation. Here, let's get it back. Doesn't matter which one you use them. They're both the same. All right. Cool.
Would that be the same for IL and IA?
I'm sorry, say that one more time.
So in electrical, you have EN equals LA IL. Can that be IA?
Should it be I in? Is that what the question is?
In the
So
original,
the problem, it's written out as IA, but you said earlier it could be IL, whichever you choose.
Well, there's only one current. There's only one current through there, right? The current's not changing. It's not branching. So it doesn't really matter if you call it IA because it's just going to be IL, right? It's all the same current. That's
basically IA is equal to IL.
Yes. Yes. All right. Cool. Any other questions? All right, well, in that case, we will end with our deep thought of the week, right? So unfortunately, this time it's bad news for you guys, right? If you had $1 for every year the universe existed, you would not be even in the 50 top richest people in the world as compiled by Forbes. However, you would be in the top 90. So still pretty good considering that there's roughly 750 or 7.53 billion people on the earth. So that would put you somewhere in the top 0.0000001%. So, you know, great job. Good job, everybody. All right, so let's clear this so that you guys can answer. How is everybody feeling about class? again, right? If you're on the bottom half of the scale, I'm going to urge you guys, please come to office hours. Please speak me out. Help me to understand how I can help you. To quote Jerry Maguire, right? Help me help you. Make sure that you do something over the weekend to try to recharge. Okay, guys, make sure. It's important. It's important. I know schoolwork's important too, right? You need to do all of that, but you also need to do something for your own mental health. And finally, here you guys go. Have a great weekend if I don't see you in office hours tomorrow. A great weekend, and I look forward to actually seeing you in class next week at some point.
Which class we're supposed to be in is on the roster, correct?
Correct. If you go in LoudCloud, they call you names like Tuesday student or Thursday student. I found it to be very, very derogatory to you guys.
Very objectifying. All right, thanks, Professor. Have a good weekend.
No problem. Have a good one.
Thanks, Dr. D.
No problem.
Through the maelstrom I go.
What was that? I didn't hear what he said. All right. Jesse, you're still there. Thanks for hanging on. Appreciate it.
You're welcome. See you, Dr. D.
See ya.